Okay, this is an example that's given in the book, and it's worth looking at very carefully because it's a good example of how the point particle point of view turns out to be useful in figuring out the motion of a system using energy considerations. Remember, you use energy when you're considering changes in distance. Work is a force over distance, and you consider momentum when you consider force working in time. Okay? So suppose I have a case like this. I start off, my initial conditions is I have two masses sliding on a frictionless surface. They're 0.4 kilograms apiece. One of them is located as x is equal to 0, and one is located as x is equal to 0.6 meters. And this is where the spring is not stretched. Okay, so this is the no force position of the spring. Now, I continue to exert a 100 Newton force on this mass over here. So I reach over at this end and I'm going to pull those masses, and of course what's going to happen is that the spring is going to stretch. So there's going to be some change in potential energy due to the spring. The system is a multi-part system. It can have a potential energy, or you can just call it the spring energy. The spring's going to extend. Eventually this mass is going to start pulling along with it, and we'll have a kinetic energy due to both of these masses. Okay, if I want to look at this with the point particle idea, I have to worry about where the center of mass is. So let's start off by finding where the center of mass is. It should be pretty easy. The center of mass at the initial spot is going to be halfway between these two masses. I've got one as x is equal to 0 and one as x is equal to 0.6. Let's do it the right way. It's going to be the sum of the masses times over the total mass. So that's going to be, I've got 0.4 kilograms at 0 plus 0.4 kilograms at 0.6 meters over 0.4 plus 0.4 kilograms. So that should be equal to 0.24 kilogram meters over 0.8 kilograms, and that's equal to 0.3 meters. That's the position of the initial center of mass. And that makes sense. It's halfway between the two masses. All right? Similarly, the position of the center of mass in this case is going to be halfway between the two masses because they're equal. So halfway between 2 and 0.2 ought to be 2 and 0.2. Well, let's see, that's worked it out. That's 0.2 times 0.4 plus 0.4 times 2 over 0.8. That's equal to 0.08 plus 0.8 over 0.8. That should be equal to what? 1.1 meters. And that's the final position of the center of mass. Okay, so here's the center of mass at 0.3, and we go to 1.1. All right, I'm going to erase this. And now I'm going to ask, what is the velocity of the center of mass when we get to this point? What is the velocity of the center of mass? Well, the change in the translational energy of the center of mass is equal to the sum of the external forces times delta x of the center of mass. The only external force we have going is this 100 newtons. This is going to be 1/2 m total v final squared minus 1/2 m total v initial squared is equal to my 100 newtons times delta x center of mass, so that's going to be 1.1 meters minus 0.3 meters. Okay, so this term should end up being 80 Newton meters. If I did that right, this is 0.8, 100 newtons, so that's going to be 80 Newton meters. This is going to be 1/2 m total v final squared. And so the final velocity of the center of mass, not of the individual particles, but of the center of mass, so let me underline that, is going to be 80 Newton meters times 2 over the total mass, which is 0.8 kilograms, and then take the square root. And I'll leave that to you to calculate what that velocity is. All right? So we've got a system here in which we have two objects that are moving separately. We calculated where the center of mass was at the initial point and the final point, and then we can calculate what the velocity of the center of mass is by using the point particle principle. Okay. We can also ask the question, is how much work has been done by this 100 Newton this 100 Newton force? Because the 100 Newton force is actually pulling a distance from, let's see, 0.6 to 2 meters. And so the amount of work done here is going to be 100 newtons. The amount of force done by the 100 newtons is from 0.6 to 0.2, so it pulls through 1.4 newtons. 1.4 meters. Let's